Section 1 Introduction. We'd like to introduce a recent advancement in computer vision technology known as the segment anything model. This model is seen as a major breakthrough because it has the ability to isolate any object within an image based on a wide range of user prompts. This achievement is made possible by utilizing a transformer model trained on a vast database known as SA1B, allowing it to adeptly manage a diverse range of scenes and objects. The segment anything model represents a significant step forward and opens the door to a new challenge known as the segment anything task. This task has the potential to form the foundation of a broad range of future computer vision tasks due to its versatility and potential. However, practical applications of this task remain a challenge due to the heavy computational resources needed to operate the transformer (VIT) models at the heart of its architecture. These models are resource-intensive compared to their convolutional counterparts, making them difficult to deploy in real-time applications. This limitation is a significant barrier to the progress and potential of the segment anything task. Recognizing the high demand for the segment anything model in industrial applications, we've designed a real-time solution for the segment anything task, which we're calling FAST. We've achieved this by splitting the task into two sequential stages: all-instance segmentation and prompt-guided selection. In the first stage, we use a convolutional neural network (CNN)-based detector to produce segmentation masks of all instances in the image. The second stage then identifies the region of interest corresponding to the prompt. Thanks to the computational efficiency of CNNs, we show that a real-time segment anything model is feasible without significantly compromising performance quality. We hope our method will make it easier for industries to adopt the segment anything task. Our proposed FAST model is built on YOLAV8seg, an object detector equipped with an instance segmentation branch, which uses the YOLACT method. We have also used the extensive SA1B dataset. By training this CNN detector on just 2% of the SA1B dataset, it performs comparably to the segment anything model but requires significantly fewer computational resources, enabling real-time application. We have also demonstrated its performance on a variety of downstream segmentation tasks. We've achieved a performance score of 63.7 at AR1000 on the MS COCO object proposal task, an improvement of 1.2 points compared to the segment anything model with 32 by 32 point prompt inputs. Our model also operates 50 times faster on a single NVIDIA RTX 3090. The real-time segment anything model is valuable for industrial applications and can be used in various scenarios. Our approach offers a practical solution for a wide array of vision tasks at a speed tens or hundreds of times faster than current methods. This could offer new perspectives on large model architecture for general vision tasks. We believe that specific models will continue to offer better efficiency-accuracy trade-offs for specific tasks. In terms of model compression, our approach shows that it's possible to significantly reduce computational effort by introducing an artificial prior to the structure. In summary, our contributions are as follows. We've introduced a novel, real-time CNN-based solution for the segment anything task that significantly reduces computational demands while maintaining competitive performance. We've conducted the first study of applying a CNN detector to the segment anything task, offering insights into the potential of lightweight CNN models in complex vision tasks. We've provided a comparative evaluation between the proposed method and the segment anything model on multiple benchmarks, which offers insights into the strengths and weaknesses of the approach in the segment anything domain. Section Summary. The segment anything model is a powerful vision foundation model that can segment any object within an image. However, its practical applications are limited due to the heavy computational resource requirements associated with its architecture. In this paper, the authors propose a real-time solution for the segment anything task, FAST, which decouples the task into two sequential stages and leverages the computational efficiency of CNNs to achieve comparable performance to the segment anything model with drastically reduced computational and resource demands. The proposed approach offers a new, practical solution for a large number of vision tasks at a really high speed and demonstrates the feasibility of significantly reducing computational effort by introducing an artificial prior to the structure. Section 2 Preliminary. In this initial section, we'll cover the basics. We're going to talk about the segment anything model and define what we mean by the segment anything task. The segment anything model is a big step forward in the dynamic world of image segmentation, a type of computer vision task. This model stands out because of its unique training process and its strong performance when working with large, visually diverse datasets. It can segment images with high accuracy, and it does so without needing to know the specific class or type of the object in the image. This model has demonstrated exceptional adaptability and proficiency in what are known as zero-shot tasks, which are tasks it wasn't directly trained on. The segment anything model is more than just a tool for segmentation. It's an example of a foundation model, which is a kind of machine learning model that can be applied to a broad array of tasks. In this case, it's showing us what's possible when we apply these versatile models to understand images in an open-ended or open-world setting. While we're very pleased with the performance of the segment anything model, it's important to note that it has its limits. The most significant of these is that it can't process images in real time. This means it's not the best choice for situations where you need immediate results, and this limitation can reduce its applicability in some scenarios. Section summary. The segment anything model is a significant innovation in image segmentation due to its high precision, class-agnostic segmentation performance and exceptional adaptability across a variety of segmentation tasks. However, it lacks real-time processing capability, which limits its wide application in scenarios where immediate segmentation results are critical. Section. Segment anything task. The segment anything task is a procedure in which an effective segmentation mask is created in response to any type of prompt. These prompts can include sets of foreground or background points, approximate bounding boxes or masks, free-form text, or any other kind of information that points out what part of an image should be segmented. Our discovery is that, in most practical applications, this task can be divided into two stages. The first stage involves identifying and segmenting all objects in the image, similar to a process known as panoptic segmentation. The second stage relies on the prompts provided to distinguish the specific object or objects of interest from the segmented panorama. Separating this task into two parts greatly reduces its complexity, which enables us to suggest a real-time, segment anything model. Let's discuss our methodology. The proposed method, FAST, is comprised of two stages: all-instance segmentation and prompt-guided selection. The first stage sets the groundwork, and the second stage is essentially a task-oriented post-processing. Unlike the end-to-end transformers, our method includes several human priors that are aligned with vision segmentation tasks, such as the local connections of convolutions and the strategies for assigning objects relevant to the receptive field. This makes it uniquely suited for the vision segmentation task and allows it to converge faster with fewer parameters. Section summary. The segment anything task involves producing an effective segmentation mask given any form of prompt, which can be detected and segmented into objects in the image. This task can be broken down into two stages: detecting and segmenting all objects in the image, and separating the specific objects of interest from the segmented panorama using provided prompts. The proposed method, FAST, consists of these two stages and introduces human priors tailored for the vision segmentation task, making it converge faster on fewer parameters. Section. Model architecture. We've evolved the structure of YOLOV 8 from its predecessor, YOLOV 5, by incorporating key features from recent algorithms such as YOLOX, YOLOV 6, and YOLOV 7. The core and intermediary stages of YOLOV 8 replace the C3 module used in YOLOV 5 with a more advanced C2F module. We've also updated the head module to have a split structure, separating the classification and detection components and moving from an anchor-based approach to an anchor-free one. In addition, YOLOV 8 has a special version called YOLOV 8 Seg, which applies principles from YOLACT for instance segmentation. This process starts with extracting features from an image using the backbone network and the feature pyramid network, FPN, which integrates features of various sizes. The outcome of this process is sent to two branches, the detection and segmentation branches. The detection branch provides category and boundary box information, whereas the segmentation branch produces a set of templates, by default 32 in the FAST version, along with corresponding mask coefficients. The two tasks, segmentation and detection, are performed in parallel. The segmentation branch uses a high-resolution feature map which keeps spatial details and also includes semantic information. This map goes through a series of convolution layers for processing, scaling up, and finally, outputting the masks. The mask coefficients, much like the detection head's classification branch, range between -1 and 1. The final result of the instance segmentation is obtained by multiplying the mask coefficients with the templates and summing them. YOLOV 8 is versatile, capable of handling a wide array of object detection tasks. The instance segmentation branch has led to the creation of YOLOV 8 Seg, which is especially apt for the segment anything task that aims to detect and segment every object or region in an image, without any regard to the object category. The templates and mask coefficients offer a great deal of flexibility for prompt guidance. As an example, we've trained a simple encoder-decoder structure with various prompts and image feature embeddings as input and mask coefficients as output. For the all-instance segmentation stage, we have opted to use the YOLOV 8 Seg method directly in the FAST version. While further design tweaks could potentially lead to additional enhancements, we consider that beyond the scope of this work and will save it for future exploration. Section Summary. The YOLOV 8 model architecture builds on YOLOV 5 and incorporates design elements from YOLOX, YOLOV 6, and YOLOV 7. It features a decoupled structure for the head module, anchor-free instead of anchor-based, and instance segmentation using YOLACT principles. The segmentation branch outputs K prototypes and K mask coefficients, which are multiplied to obtain the instance segmentation result. YOLOV 8 seg is suitable for segmenting any object or region in an image, and the prototypes and mask coefficients offer extensibility for prompt guidance. Section 3.3 Prompt Guided Selection. In Section 3.3, titled Prompt Guided Selection, we discuss the second part of our Segment Anything task, following the initial segmentation of all objects or areas within an image, achieved through the use of YOLOV 8. This subsequent stage involves employing several prompts to help pinpoint the specific object or objects we're interested in. The types of prompts we use include point prompts, box prompts, and text prompts. Let's talk about point prompts first. These involve associating the points we've chosen with the variety of masks we generated during the first phase. The main objective here is to identify which mask contains the point we're looking at. To do this, we use the same method as described in some prior works, utilizing both foreground and background points as our prompt. There may be situations where a single point in the foreground falls within several different masks. In such cases, we can make use of background points to help us rule out any masks that aren't relevant to our current task. By leveraging a combination of foreground and background points, we can select multiple masks that fall within our area of interest. Once we have our masks, we combine them into one to fully delineate our object of interest. To enhance the efficacy of this mask merging process, we also apply what's known as morphological operations, which are procedures that manipulate the structure of an image. Section Summary. In the second stage of segmenting objects in an image using YOLOV 8, prompts such as point, box, and text are used to identify specific objects of interest. The point prompt involves matching selected points to masks obtained from the first phase to determine the mask in which the point is located. By using foreground, background points, multiple masks within the region of interest can be selected and merged into a single mask to mark the object of interest, with the help of morphological operations. Section Box Prompt. We start by focusing on a process known as intersection over union, IOU, matching. This procedure involves comparing a chosen rectangular area, or box, to different boundary regions, or bounding boxes, that were identified during the initial stage of the process. Our goal here is to find the boundary region that has the greatest overlap, or highest IOU score, with our chosen box. This way, we can pinpoint and select the object we're most interested in. Let's shift our attention to the text prompt now. In this situation, we first extract the text embeddings, or representative numerical values, from the given text, using a model called clip. Once we have these embeddings, we can find the corresponding image embeddings. With these image embeddings at hand, we start matching them to the inherent characteristics of each boundary region, using a measure of similarity. We look for the boundary region that is most similar, or has the highest similarity score, to the image embeddings of the text prompt. That's the one we select. By diligently applying these prompt-based selection methods, FAST, our tool, can consistently pick out specific objects of interest from a segmented image. This approach offers a speedy and effective solution for segmenting anything in real time, which significantly boosts the practicality of the YOLOV 8 model for complex image segmentation tasks. Of course, there's always room for improvement, and we plan to explore even more efficient prompt-based selection techniques in the future. Section Summary. In order to select the object of interest from a segmented image, we perform intersection over union, IOU, matching between the selected box and the bounding boxes corresponding to the various masks from the first phase. For text prompts, we extract the corresponding text embeddings using the clip model and match them to the intrinsic features of each mask using a similarity metric to select the mask with the highest similarity score to the image embeddings of the text prompt. These prompt-guided selection techniques enable the FAST to reliably select specific objects of interest from a segmented image, making the YOLOV 8 model more efficient for complex image segmentation tasks. Section 4 Experiments. In this section, we'll be delving into the experimental evaluation of FAST. Initially, we'll examine FAST's runtime performance to ascertain its effectiveness. We'll then set out to test it with 4 distinct tasks that do not require prior knowledge, or so-called zero-shot tasks. We'll also study how it performs in practical situations, its efficiency, and the ease of implementing it. Our initial experiments are aimed at comparing the functional abilities of FAST with another unspecified system. Mirroring the other system's test approach, we'll be carrying out 4 tasks, each requiring varying degrees of complexity. At the low level, we'll focus on detecting edges, at the mid-level, our task will be generating object proposals. At the high level, we'll engage in instance segmentation and, finally, at the same high level, we'll segment objects using free-form text input. These tasks will not only test FAST's capabilities but also provide us with further evidence of its practical application potential and speed. Let's dive into some specifics of our implementation. Unless otherwise noted, we will adhere to the following conditions. Firstly, we'll use a YOLA of 8x model as the cornerstone of FAST's architecture, with the input size set at 1024. Secondly, we'll conduct the training of FAST on 2% of the SAW1B dataset. Lastly, the model will be trained for 100 epochs, using the default hyperparameter settings with one small adjustment. We'll increase the reg_max value from 16 to 26 in the bounding box regression module. This adjustment is made specifically to enable the prediction of larger instances. Section Summary. The section describes experiments conducted to test the efficiency and capabilities of FAST, a model used for zero-shot tasks. The experiments include testing the similarity between FAST and other models, as well as testing FAST's performance on low-level, mid-level, and high-level tasks. The experiments also validate FAST's capabilities with real-world applications and speed, and provide implementation details. Section 4.1 Runtime Efficiency Evaluation. In Section 4.1, we evaluate the efficiency of the algorithm in real time. This algorithm uses the transformer architecture, a versatile framework that can represent numerous mapping functions for various tasks. To segment any object, the algorithm learns a vision-centric inductive bias through training on large-scale data. In contrast, FAST, which is built with a human pre-knowledge in structure design, results in a more compact model. From the figure, we can see that FAST produces quite satisfactory results. Looking at the table, we compare the running speeds of the initial algorithm and FAST on a single NVIDIA GeForce RTX 3090 GPU. The results show that FAST outperforms the initial algorithm across all numbers of prompts. Moreover, FAST maintains a consistent running speed regardless of the number of prompts, making it the preferred option for the everything mode. Moving on, we evaluate FAST on the fundamental low-level task of edge detection using the BSDS 500 dataset. To do this, we first select the mask probability map from the results of FAST's all-instance segmentation stage. We then apply Sobel filtering to all mask probability maps to produce edge maps. Our evaluation concludes with the edge non-maximum suppression (NMS) step. Section Summary. The paper evaluates the runtime efficiency of an end-to-end algorithm that uses the transformer architecture for segmentation. The FAST model, which incorporates human priori knowledge in structure designing, generates relatively satisfying results and outperforms the transformer model in terms of running speed on a single NVIDIA GeForce RTX 3090 GPU. FAST is also assessed on the basic low-level task of edge detection using BSDS 500. Section Results. The results from our study are shown in a graphical format in figure. The first thing that stands out when looking at the data qualitatively is that the FAST model, despite having significantly fewer parameters, only around 68 million, is capable of producing a commendable edge map. When compared to the benchmark or ground truth, both FAST and its counterpart seem to predict a greater number of edges, even identifying some that aren't documented in the BSDS 500. This inclination is numerically represented in a table. This table indicates that our performance is on par with the counterpart model, particularly noted by a higher R50 value and a lower AP value. The process of generating object proposals has been a foundational step in numerous computer vision tasks for quite some time. This includes tasks like general object detection, few-shot object detection, and image understanding. Several well-known proposal generation methods have been a part of the evolution of visual recognition over the past few decades, essentially serving as a crucial step in visual recognition methods. Some of these proposal generation methods include EdgeBox, geodesic, selective search, and MCG. Recently, many methods based on deep learning have been proposed, such as DeepMask and OLN. As an instance, RCNN series object detection methods use the selective search method, while the newly proposed open-world detector, UniDetector, employs the OLN method. However, most current object detectors use RPN, which is limited as it can only generate object proposals for the categories it has learned. This hampers its usage in open vocabulary recognition tasks. Hence, generating object proposals that can work without prior knowledge, or zero-shot, is of great importance. The quality of the proposed method is vital for achieving high performance in these visual recognition tasks. In our research, we employ the bounding boxes generated in the initial stage of the FAST model as the object proposals. To gauge the performance, we ran tests on both the LVIS and COCO datasets, sticking to the existing evaluation methods. Moreover, we also tested the accuracy of mask proposals. For this, we used all instance masks from the first stage, as per the experimental parameters of the previous studies. Section Summary. The section discusses the importance of object proposal generation in computer vision tasks and the evolution of proposal generation methods. The paper evaluates the performance of FAST, a proposal generation method with fewer parameters, and finds that it produces a generally good edge map, but tends to predict more edges than the ground truth. The generated bounding boxes of FAST are used as object proposals and tested on LVIS and COCO datasets. Section Details. We're sharing our findings on FAST and VitDet's performance on the LVIS dataset. Unfortunately, we weren't able to access VitDet's detailed evaluation process. Instead, we gauged category-agnostic mask and box recall using the official LVIS evaluation code. We couldn't replicate VitDet's mask AR results as shown in its original paper, but we believe our evaluation effectively showcases how FAST stacks up against VTDET. Now, let's discuss our results. We found that our method offers a significant edge when it comes to generating box proposals. Our findings, illustrated in tables 1, 2, and 3, include the average recall, AR, of various methods on the COCO validation set. Here's what we found. Some methods, like edge boxes, geodesic, selective search, and MCG, do not require training. Deep mask and OLN, on the other hand, are supervised methods that train on VOC categories within the COCO training set before testing across all categories. Our approach, along with VTDET, employs a fully zero-shot transfer. Our method and VTDET don't fare as well in R at 1.0 precision compared to previous supervised methods like OLN. However, in R at 1.000, our method significantly outperforms OLN. This is because previous methods were trained on certain categories in COCO, which resulted in them having higher confidence levels in these categories during inference. In contrast, our method and VTDET, being zero-shot, result in balanced confidence levels across different categories. This allows us to recall more categories not present in COCO. You can see more comparisons in Figure 1. In Table 2, we display the bounding box R at 1.000 results of VitDET H, FAST, and our method on the LVIS V1 dataset. Our method significantly outperforms the most resource-intensive model of FAST, the FAST HE64, by over 5%. However, it doesn't quite match up to VitDET H, which was trained on the LVIS dataset. The reason for these results is that we used ground truth bounding box information as a supervisory signal during our training process. FAST, in contrast, used only the mask as a supervisory signal, generating its bounding box at inference by extracting the outer box from the mask. Lastly, from Table 3, our method's mask proposal generation shows a lower recall rate. We attribute this mainly to our segmentation mask's inability to finely delineate small-sized objects. We delve into more detailed discussions in Section 4. Section Summary. The authors report the results of their FAST method on the LVIS dataset, which outperforms the most computationally intensive model of VTDET H by over 5%. However, it falls short compared to VTDET H, which was trained on the LVIS dataset. The authors also note that their method has a significant advantage on the box proposal generation tasks, but their mask proposal generation is relatively lower on recall due to segmentation mask issues on small-sized objects. Section Approach. In our approach to instance segmentation, we make use of bounding boxes created by VTDET as guides. In line with our explanation in the previous section, we select the mask that shares the largest overlap with the bounding box, as determined by the intersection over union (IOU) measure. This chosen mask is then identified as the predicted mask. The results of this process are detailed in the table. Unfortunately, our results in this task do not exhibit a high average precision, AP. We suspect the reasons for this could be related to the accuracy of the segmentation masks or the strategy we employ in choosing masks based on the bounding box. Some examples of this are provided in the following section. In our final approach, we raise the bar further and attempt to segment objects using free-form texts. The aim of this experiment is to demonstrate the FAST system's ability to process text prompts efficiently. Unlike other methods, FAST does not require alterations in the training process. It operates by first running the text through the CLIP's text encoder, generating a text embedding. This text embedding is then used at inference time to find the most similar mask. In terms of results, we've presented some qualitative outcomes in the figure. FAST proves capable of segmenting objects well based on the text prompts. However, the process speed for text-to-mask segmentation is less than ideal. This is due to the necessity of feeding each mask region into the clip feature extractor. One intriguing challenge yet to be solved pertains to how we might integrate the clip embedding extractor within FAST's backbone network in order to achieve model compression. Section summary. The instance segmentation task is accomplished by using the bounding box generated by VT-det as the prompt, and selecting the mask with the highest IOU with the B-box as the predicted mask. However, the evaluation results show a low AP, which may be due to segmentation mask accuracy or the box-based mask selection strategy. Additionally, the FAST model can segment objects based on text prompts, but the running speed of the text-to-mask segmentation is slow, and integrating the clip embedding extractor into the FAST's backbone network is an interesting problem for model compression. Section 5. Real-world applications. In this part of our research, we tested our algorithm, FAST, in a variety of real-world applications to assess its efficacy and understand its pros and cons. We also compared it with other established methods and the ground truth to provide a comprehensive review. This assessment involved visual illustrations of FAST segmentation capabilities across different modes: point prompt, box prompt, and the everything mode. One application we focused on was anomaly detection, a process that distinguishes between normal and flawed samples in manufacturing processes. We tested FAST using a specialized dataset for anomaly detection, or AD. The results showed that FAST, when operating in the everything mode, was able to distinguish nearly all areas comparable to other methods, but with a slightly lesser degree of accuracy. We also noticed that FAST's background masking did not cover the entire backdrop, a characteristic inherent to the YOLACT algorithm it's built upon. However, by using foreground or background points, signified by yellow and magenta points in FAST point, or a box-guided selection, FAST was able to precisely segment the defective regions. The second application we explored was salient object segmentation, whose goal is to isolate the most eye-catching objects in an image. This task differs from semantic segmentation as it is not concerned with classifying the object. To assess FAST's performance in this task, we applied it to a well-known dataset, RedWeb-S. Our findings showed that FAST, while operating in the everything mode, had slight variances from other methods as it segmented fewer irrelevant background objects. When we employed point-guided selection, using yellow points in FAST point, we obtained masks for all objects that caught the eye. The segmentation results of FAST point were virtually the same as other point-based methods and the ground truth, except for minor detail loss at the edges. We could also select the object of interest using a box prompt, as shown by the green box in FASTbox. However, we found it impossible to select multiple objects using a single box, a limitation shared by other box-based methods. Section summary. The performance of FAST is evaluated across different application scenarios, including anomaly detection and salient object segmentation. Under the everything mode, FAST can segment nearly all regions but with a lower level of precision compared to ground truths. By using foreground, background points or box-guided selection, FAST can accurately segment the exact defective regions or objects of interest. Section: Building Extracting. We are focusing on the section of the paper that discusses the performance and applications of the proposed method called FAST for building extraction from optical remote sensing imagery. This technique has various applications, including urban planning. To evaluate the effectiveness of FAST, we used a dataset introduced by a previous study. Our results, shown in figure, reference to the figure, indicate that FAST performs well in segmenting regularly shaped objects. However, it tends to segment fewer regions associated with shadows compared to another method we compared it with. Additionally, we introduced two methods called FastPoint and FastBox that allow the selection of regions of interest using point prompt and box prompt techniques, respectively. In FastPoint, we position a point within a shadow region. Despite this, we can still obtain the correct mask for the building by merging based on this point. This demonstrates that our method can handle noise interference to some extent. In terms of performance, FAST achieves comparable results to the method we compared it with, while being significantly faster. It runs 50 times faster than the 32x32 method and 170 times faster than the 64x64 method. This makes FAST a suitable choice for various industrial applications, including road obstacle detection, video instance tracking, and image manipulation. Interestingly, on certain images, FAST even produces better masks for large objects, as illustrated in figure, reference to the figure. Section summary. The paper discusses the use of FAST for building extraction from optical remote sensing imagery, which has applications in urban planning. FAST performs well in segmenting regularly shaped objects, but segments fewer regions related to shadows. The method can resist noise interference and runs much faster than other methods, making it a good choice for industrial applications. Section: Weakness. In our experiments, we observed a weakness in our approach. While our box generation showed a significant advantage, our mask generation performance was not as strong. We illustrate this with examples in figure, reference. Specifically, we found the following characteristics in the FAST model. 1. Low quality and small-sized segmentation masks received high confidence scores. This can be attributed to the fact that the confidence score is defined based on the B-box score of Yolov 8, which is not strongly correlated with mask quality. One way to improve this is by modifying the network to predict the mask intersection over union, IOU, or other quality indicators. 2. Masks of tiny-sized objects tended to be square-shaped. Additionally, the masks of large objects sometimes exhibited artifacts along the borders of the bounding boxes. This represents a weakness in the YOLACT method. However, this problem can be addressed by enhancing the capacity of the mask prototypes or by reformulating the mask generator. Furthermore, it's important to note that our model's performance could be further improved by utilizing more training data. Currently, we only use 1/50th of all SAW-1B datasets, so incorporating additional training data has the potential to enhance the model's performance even more. Section Summary. The box generation in our experiments has a significant advantage, but the mask generation performance is below par. We found that the confidence scores for low-quality small-sized segmentation masks are large, which is not strongly related to mask quality. The weakness of the YOLACT method is that the masks of some tiny-sized objects tend to be near the square, and the masks of large objects may have some artifacts on the border of the bounding boxes.